Hello everyone, my name is Álvaro and I am a PhD candidate at the University of Colorado Boulder, where I study how can we use electromagnetic fields in order to control multi-phase flows in microgravity. One of the most recent applications of this work is our new magnetically enhanced electrolysis concept that we are going to present today. But before, let's give a bit of context to it. This presentation was given during the ASGSR meeting 2021, almost 1 month ago. And it was a fantastic conference with tons of good questions and good interaction. And a lot of people essentially was interested in this work. So we thought that it would be good to give a virtual presentation besides the in-person presentation that we gave in Baltimore. This work is a joint effort with Connor Nogales, Keith Billings, Dr. Will West, and Dr. Hans-Peter Schaub. We are teaming up to develop a payload that will fly on Blue Origin's new Zephyr thanks to the ASGSR Souza program 2020. And what we are presenting here is the post-PDR design update on our magnetically enhanced electrolysis payload. Today, I want to go over a bit of context of this research about the motivation. I'm going to talk about our payload and the tests that we are carrying out on it, and essentially the future plans, the near future plans that we have for the development of this magnetically enhanced electrolysis concept. So first of all, talking about introduction and motivation. What led us to develop the magnetically enhanced electrolysis concept was realizing that the current systems that deal with the low gravity electrolysis and in general any kind of low gravity phase separation system are highly inefficient. So for instance, if you take a look at the oxygen hydration assembly at the ISS, you will see that besides the electrolytic cell, which is the core of the assembly, the device that separates water into hydrogen and oxygen, you have all sorts of ancillary components like pumps, controllers, centrifuges that separate phases that are extremely inefficient. From a space engineering perspective, this is the closest you will have to a nightmare. It is an extremely complex system, it is heavy and it consumes power and imparts vibrations, which are, I guess, far from convenient for all the instruments around this oxygen generation assembly at ISS. But all those devices are necessary because if you don't do anything, you will see that something like what happens here at the left happens in microgravity, right? Since in microgravity you don't have active buoyancy acting on the system, a layer of bubbles and gases will tend to appear over the surface of the electrodes. And the main consequence of this is that you will shield your active surface, reducing drastically the efficiency of your system. And you will also need a mechanism to induce phase separation. So working on low gravity hydrodynamics, which is this approach that I had described where we use magnetic fields to control multi-phase flows in microgravity, we thought about new ways to do this. And in order to make this even clearer, what we use is what is called the diamagnetic force. The diamagnetic force has been used on Earth, for instance, in there, a frog, being levitated by the diamagnetic force that is exerted by a huge coil. It is that you can polarize water, magnetically polarize water, and that results in a do this kind of very funny experiments with living organisms, who, by the way, doesn't seem very happy about it. The difference is in that microgravity, you don't have to counteract the force of gravity. So even your system, and that's the key point of our application. So what we want to do is to use permanent magnets, permanent neodymium magnets, which are particularly powerful, to essentially assert this diamagnetic force on our system in such a way that we pull the water and we push the water and we pull the bubbles out of it. The idea is that the bubbles have a gas inside them, have a much weaker magnetic response. So we are kind of generating some sort of local gravity effect thanks to the magnetic potential. How good is this? Well, if you take a look at this simulation where you see an asymmetric cut of a magnet of 1 by 2 centimeters, more or less, a cylindrical magnet, of course, you will see that the terminal velocities, that is the steady state velocity of the bubbles that are within the liquid, and I'm talking here about more or less a 1 millimeter radius bubble, will be of the order of 0.1 to 10 millimeters per second. That in microgravity conditions is a very significant value that we want to use to separate phases. Another effect that we also employ is the Lorentz force. The Lorentz force appears when you have a charge in movement subject to a magnetic field, as most of you probably know already. So the idea of the Lorentz force is that by inducing a significant magnetic field to a pair of alkaline electrodes, you can take advantage of the current that is flowing through the system to induce this magnetic buoyancy effect. And this magnetic buoyancy effect can be used to remove the bubbles from the system. And even though it is more complicated, maybe in the future also to induce phase separation. So two different mechanisms, the magnetic force and Lorentz force. Both of them can be useful in space applications because of the absence of gravity. The magnetic force is weaker, but much more controllable. The Lorentz force is stronger, but it's hard to control in a technical scenario. And our experiment uses both concepts. But before we go to the description of the experiment, let's talk about Blue Origin's new Zephyr suborbital rocket. As you have probably seen in TV several times, new Zephyr looks like that, and the payload area is mounted on the top. The payload is a cabin that has several racks, by nanoracks, and each one of those racks has a small mini payload of 0.5 kilogram of mass and 2 units. That is the payload that we are flying in the rocket. One thing that makes this rocket so special is that it gives us 3 minutes of high-quality microgravity conditions. Just to give you a reference, Sarmstorff Tower in Bremen, for instance, gives us around 9.3 seconds. The shaft at Glen gives about 4 seconds. So having 3 full minutes of microgravity conditions is fantastic for testing any kind of system in microgravity. You have high quality conditions and you have a long-term exposure of your system. How easy or how hard is it to simulate to develop a payload for this kind of platform? Our scientific objectives for our experiment are to, first of all, assess the capability of modern neodymium magnets to induce liquid gas phase separation, and to passively detach the hydrogen and oxygen bubbles that are generated at electrodes, to study the performance of this magnetically enhanced buoyancy system on our electrodes, and to do that we measure the voltage and current flowing through each electrode. And we also want to analyze the dynamics of bubbles in low gravity. The result, after evaluating several architectures and several ways to do that, is what you can see at the right. You essentially have an upper electrolytic cell assembly where you have a magnetic force being acting on the system, and we have a control cell at the bottom that doesn't have any kind of magnetic interaction. We see both systems by means of this red camera that is observing them with these mirrors in there. And we control everything with an electronic board that we have designed for this experiment. And all of this has to weigh less than 0.5 kilogram. As I mentioned before, how hard is it really to design something like this? If you have if you read the payload requirements that are publicly available, this is what you find. You will have 150 milliliters of approved non-hazardous liquids with 2 layers of containment. You will need to limit yourself to 0.5 kilogram, avoid any kind of radio frequency transmitters or engines or anything similar to that, and you have power limitation of 4.5 watts. As you can imagine, these are very stringent requirements, and these are very stringent because it's very hard to develop a payload of 2 units with just 0.5 kilogram of mass. That is the main thing. But then, of course, you have the two layers of containment, of which we will talk later. Also, you need to ship the payload 2 weeks before the flight to Van Horn, Texas. And that adds another level of complexity because in other facilities like Sarmstorff Tower, you can interact with your payload until essentially 2 hours before the launch. So as I said, we evaluated several architectures and we came up with this one. This one is essentially magnetic proton exchange membrane, as I mentioned, sorry, not proton exchange membrane because we changed the design in the middle of the process. A magnetic cell, a magnetic assembly where some magnets impart a force on your system and is supposed to enhance your performance and also to induce phase separation. Good. Then you have the control cell, the camera, the mirrors, a sponge at the bottom of the system in case there are any leaks, 2 layers of containment. One important thing is that since we cannot use hazardous liquids, we have to use an electrolyte that is a potassium sulfate instead of the usual sodium hydroxide or potassium hydroxide. And the reason for that is that those 2 electrolytes are harmful, they are corrosive, so we cannot use them in this kind of system. What we plan to measure during the experiment, during those 3 minutes of microgravity, are the movement of the bubbles coming off from the electrodes, the current and voltage across each one of the cells that we are measuring, and the characteristic intensity and voltage curve of each electrolytic cell. Let's go into detail about the magnetic assembly. Our magnetic assembly is composed of those essentially three elements. First of all, the place where the bubbles are generated. In this case, there are only two electrodes in here. And we consider to use proton exchange membranes, but proton exchange membranes are very sensitive to water impurities. And we had many issues with them during the 5 months that we were using them. We essentially couldn't guarantee that they would resist for 2 weeks once the experiment was shipped to Blue Origin. So we decided to switch the system to an alkaline electrolysis cell that uses an electrolyte of, as I said, potassium sulfate. So we have the surfaces where the oxygen and nitrogen bubbles are generated, which are here in the middle. Of course, they have to be separated by a membrane to prevent the explosive recombination. Then you have these two big magnets. Well, actually not so big. It's 1 inch by half an inch, I think, something like that, a cube like that. But you can see it to scale with this penny here. And the idea of the magnets is that they generate a magnetic field that pulls the bubbles from the electrode and brings them to a bubble collector that you can see here. The idea is that the bubbles accumulate there, and then they fly, or they are sucked by these channels in here that bring them to those phase separators. For those of you who are not familiar with low gravity fluid mechanics, you should know that water in space likes the corners and feels afraid from the round geometries that you can see here. So the idea is that if we have a mixture of water, at least in the beginning, we will have a mixture of water and gases coming to this system. The liquid will remain at the bottom and the gas will go to the surface. And this is a pretty common mechanism called corner geometries, or essentially corner geometries, that is used in all sorts of microfluidic and low gravity fluid mechanics applications. So this is the idea, right? We generate the bubbles, we remove the bubbles with the magnets, and in that way, we can improve the efficiency of our system. In particular, the magnetic field, what does is pulling the bubbles from these two surfaces or these two electrodes, and the bubbles come following these lines and reach the magnet. These are the accelerations that we expect to exert. We are talking about not about accelerations, sorry, velocities. We are talking about 1 millimeter per second at the top of the upper electrode and 0.1 millimeters per second at the bottom. In this way, we have essentially 2 points of data, two systems subject to different accelerations that we can compare. We can remove between 0.6 and 6 centimeter cube per minute of bubbles at the surface of the electrode. And we also have an added effect, which is the Lorentz force electrolysis. The magnet's mass is 61 kilograms, which is at 12% of the total weight. And as you can see here, we have essentially two modes of operation: a pulling force that is normal to the electrode, and a shear force at the bottom that is perpendicular to the electrode. And this is just again to have 2 points of comparison. The phase separators not only work based on the pure capillary regime fluid mechanics, there's also an added magnetic force that pushes the water to the bottom of the cell. So if there is a very small bubble that gets trapped in the middle between the two walls, the magnetic force will tend to bring it to the surface. That's something pretty cool that we also proposed in a previous paper. Why the non-magnetic assembly is located below? Well, the reason is that if you compute acceleration contours, you will see that the microgravity level is reached at more or less 5 centimeters from the magnet. So we have decided to put the cells at about 9 centimeters to make sure that the control cell is not subject to any kind of magnetic interaction. That implies also that we have this distance, right? We need this distance between the two electrodes. So we need a way to see both of them. And the complication here is that such a small system, 10 by 10 by 20 centimeters, needs a small camera, and small cameras don't have variable focal lenses or anything that is as fancy as that. So we needed to design a system where the camera was able to visualize and focus both planes simultaneously. And that implies that the optical paths between the camera and the system has to be the same. The optical lens has to be the same. And the solution we came up with, after considering different alternatives, was using mirrors. And by using mirrors, what you get is this kind of image where you can see almost perfectly both electrode assemblies from a single point, saving mass and saving mass on a second camera, and saving complexity. And this is how the system looks like with the two electrodes and and the two electrode assemblies and the two mirrors in here that allow us to see both of them. Right now, the system looks like this. We have this magnetic cell and the magnetic cell again, the mirror supports, the magnets, everything. And here you can see the alkaline electrodes that are more or less 1 centimeter square each. You can see them in the magnetic cell and in the non-magnetic cell. And again, the idea is that the gases will go from this surface toward the magnets. They will come out following these tubes and they will reach the gas separators that in this image are partially filled with water. And you can see here the meniscus of the liquid caused by this corner geometry and how the liquid, well, this is how you see it on Earth, but in microgravity it will be the same. The liquid will tend to remain at the bottom of this little tank. Some of the tests that we have carried out, of course, are based on our electronics. We have tested the electronics thoroughly that were designed by Connor, brilliantly designed because we have been able to save a lot of mass and a lot of power thanks to this implementation. You have our Raspberry Pi that we use for the camera and for taking the measurements, and some digital analog converter here that we use for the temperature sensor. The idea is that with this electronic board, we can control the current flowing through its cell. Controlling the current is important in the electrolysis community. It is usually preferred to have constant current cells instead of constant voltage, and that we are essentially doing that. And we have the voltage as a control variable. We have been able to test it in the flight sequence, and it is working like a charm. We are very happy with its performance. And in fact, you can see here how we can control the current flowing through each cell and how we can observe and measure the voltage through each of them, which is a pretty useful metric because it essentially tells us how efficient the bubble removal process is happening. And if you take a close look at this plot in there, you will see this little high frequency in respect to the total test, but actually it is a low frequency component, which is indeed related with the presence of bubbles in the system. So when the bubbles appear, the electrodes are masked and the efficiency drops. And that is exactly what we want to see during the experiments. One of the challenges has been to build those 2 layers of containment. We have imposed ourselves a requirement of 10 psi. So our system has to be able to withstand 10 psi, which is almost 4 times the maximum pressure difference that we had during the flight. The first layer of containment, which is essentially those 2 assemblies that I described before, is working perfectly. There are no leaks. The few we could detect were solved, and it is working very reliably. The second layer, though, that is this kind of black bag that we put outside of the system, is giving us some trouble. And right now we are testing different materials because essentially every time we put 10 psi on it, we blow up the assembly. So one thing we are testing right now, for instance, is mylar instead of thermoplastic. You know that mylar can be thermosealed, so it is pretty convenient for this kind of application. And at the same time, mylar is usually graded for more than 70 psi. So waiting for the materials right now, and if we are lucky, you will see. The essential idea is to use a plastic bag like this that we're representing here to hold the whole assembly and then inflate the bag and see with a constant pressure if we essentially can withstand the pressure of the system. Some conclusions about this are that, first of all, in terms of fundamental motivation, the phase separation process in every space application accounts for significant mass and power penalties. And in particular, in low gravity electrolysis or even low gravity boiling, this may be addressed by means of diamagnetic buoyancy. Diamagnetic buoyancy, which is the effect that magnets induce in water for being a diamagnetic material. The ASGSR Souza 2020 experiment is a technology demonstrator that will try to validate and study this concept during a long-term exposure to microgravity conditions. At the time of writing, the design of the payload is complete, and we are testing our system and improving our layers of containment. The big challenge of this system is to ensure that we satisfy the mass budget while maximizing the capabilities of the full system and the PCB controller. So essentially, we are trying to do the most we can with as little as we can. I want to acknowledge at this point our department at the University of Colorado Boulder, the Aerospace Engineering Sciences Department, ASGSR for giving us the chance to fly this payload, of course, Blue Origin, who is flying and supporting us in the development of this experiment, NASA GPL, in particular Keith Billings and Dr. Will West for their tremendous support through this year, Lacacia Foundation for financing this experiment, and Bioserve Space Technologies for kindly giving us access to their facilities and giving us access to a lot of material that we have used to essentially test and build our payload. So that was it from me for today. Please, this is an ongoing project. If you have reached out at any of these links, and we will be more than happy to talk with you and discuss potential avenues for collaboration. Your disposal for any comments. Thank you.